Morning, everyone. Let's just see while everyone tries to connect. So you guys can you guys see it? It's interesting. On my side, it's showing 0 viewers, which is off-putting, but that's fine. Feels like too much effort. In fact, you're quite lucky I'm just not wearing my pajamas still. Cool. Okay, we'll give it a minute or so and just let everyone catch up and connect onto the video. And then after that, we'll get started with everything. All right. See, real Richard, not an imposter. There should be an HD view. There's definitely not a 4K stream because I only have South African internet. It's just a Logitech camera, normal Logitech webcam. I don't know. It's got a microphone in it. Seems to work, but it's good that it's coming out nice. Yes, Carl, you can, but you have to come fetch it. Yes, but it's I promise that it's empty, and it's empty because I used it to water plants. I would never have drunken water myself. That would be sacrilegious. Cool. Alrighty then. So shall we get going? Okay. So the idea today is to talk about sorting, which is the last big topic that we have to look at. And we're going to cover a few different approaches to sorting large lists. So essentially, we're going to look at a couple of the kind of 3 almost naive algorithms that we can look at to sort some lists, and then there's some more complicated ones that give us better complexity. Okay, so the first one that we're going to look at is something called a bubble sort. Okay, and a bubble sort follows this kind of approach. Okay, so if we have a list of a couple of numbers, sorry, I still haven't managed to get a stand or something, so I'll try and hold this as still as possible. But if we have a list of numbers, say we have 42, 61, 13, 12, 5, and maybe let's go for a big number, 51. Okay, so say we've got those numbers, then what you do with the bubble sort is that you compare neighboring numbers, and if they're in the wrong order, then you swap them. So what we would do is we would start off at the beginning of this list, and we would compare 42 and 61, and we would say, are they in the correct order? Okay, and so let's say we're sorting this as an ascending list, and so what that would mean is that 42 should be in front of 61, and so we're okay with this, and so those ones get left as they are. Next thing we do is we look at the next pair of numbers, so 61 and 13, and we say, okay, no, there's definitely a problem there, and so we swap those numbers. So we would end up with 13 over there and 61 over there, just like that. We then continue on to the next one, and we now compare 61 and 12. Okay, and we say, are they in the correct order? No, they're not, and so we swap them. So we would then say that 61 moves up and 12 moves over there. Excuse me. Following that, we move on and look at the next group. And so we see 61 and 5, and we perform a swap there again. All right. And then finally, we compare the last pair, and we see 61 and 51, and so those two would swap. Just like that. Okay. Yes, this is a bubble sort. Okay. I think what I'm going to do is I'm going to rather move over to screen sharing and try and do this as a do this in like PowerPoint or something. Let's just see if that gives us a better view. Okay, so having moved over, one sec. All right. Yeah, I used to have one, and then it got old and broke. But getting a Wacom is actually a very good idea. So I'm going to try and get one for if I carry on doing videos like this. But for now, let's say we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 12, 5, and 51. Thanks. I'll go grab that fix straight away. Okay, so I've now moved on to like a PowerPoint type thing. Hopefully that'll make it better. Might be easier to work with. So let's just give this a sec so the video stream can catch up with everything, and then I'll carry on. All right. Okay, so let's carry on. Okay, so the idea is that we have our sorted list of numbers, and those would be sitting inside an array of some kind. Okay, so we now say, okay, we're going to compare two neighboring numbers. So we're going to be looking at 42 and 61, and we see that they are already in the correct order, and so we leave them and we just carry on. Okay. We then compare the next pair of numbers, and so we see 61 and 13, all right? And in this case, they would need to swap. 61 and 13. Okay, so those two have now swapped. After that, we do the next comparison, and we see 61 and 12, And so in this case, we would also want to swap because 61 is bigger than 12. Okay, so we end up doing that. We then do the next comparison. Okay, and so we see a 5 and a 61 like this. So those would also swap, 5 and 61. And then finally, we do the last one, and that gives us 51 followed by 61. Okay, and that's given us our first iteration of the main loop. And you'll see what it's done is, in effect, it's picked up the maximum number and it's carried it through to the end. Okay, it could potentially make some other changes as well, so kind of partially sorting bits and pieces beforehand. But the main thing is that it's picked up the maximum number and moved it to the very last block over here. So now that it's there, we know that the maximum number is at the end, and so we can almost say that we now don't need to go back past that. We know that the max is at the end and that it's already in the correct place. So from here, we then start again. So we go back to the beginning and we compare the first two neighboring items. Okay, so we see that 42 and 13, and so they go like that and they swap. Okay, we then do the next comparison. And so we have our 42 and our 12. We do a comparison and we would say that they swap because they're in the wrong order. We then move over and do the next comparison. And so we see 42 and 5. And we say that those are in the wrong order, and so those swap. Okay, so 5 and 42 swap like that. Okay, then after that, we do another comparison. We see 42 and 51. Those are in the correct order, and so we leave them as they are. And we've now reached our brick wall at the end, and so we're happy that we've gone far enough. All right. So now what we do is we finish that main loop again. We now know that it's picked up the next biggest number and moved it to that last spot. All right. Okay. Following that, we run our main loop again. So we say 13 and 12, those are in the wrong order, and so we swap them. We would then go and do our next iteration, and we would see 13 and 5 and say those are in the wrong order, and so we swap them. We would then do our next iteration and get 13 and 42, and we would say those are in the correct order, and so we leave them as they are, and we've now hit our brick wall at the end, and so that iteration of the loop finishes. We can see that it picked up the biggest number and made sure it was now at the end. We then start again, and we see 12 and 5. Okay, those are in the wrong order, and so those swap. All right. We then do the next comparison, and we see 12 and 13. Those are in the correct order, and so we leave them as they are. And so the main loop finishes. Finally, we do one more comparison, and we see 5 and 12, and we see that those are in the correct order, and our sort is finished. Okay. If we were to move the edge of our wall to there, we would see that that's the last one. One number by itself is considered sorted, and so that's fine. And so our loop is finished, and we can see that we now have this completely sorted. All right. Let's see any. Cool. Okay. So we are up to date on that. Okay. The idea here, we can see that there are, if you have n items in your sort, what we're doing is we're saying pick up the one, imagine picking up your maximum number at the beginning, and then you would compare it to every other number in the list. So we would end up doing n-1 comparisons on the first iteration. Okay. So on the first iteration, we do n-1 comparisons. Yeah. On the second iteration, we don't need to compare it to the very last one, but we would end up comparing it to n-2 of the different items in the list. In the third iteration, our main wall would have moved over there, and we would end up comparing it to n minus 3. Okay, and that continues all the way down. So ultimately, on our, we will end up doing n minus 1 or n minus 2 iterations, and in everything we compare it to the number of, we do enough comparisons of the numbers that are in the unsorted part of the list, okay, minus 1. And so when we're going all the way through, eventually we'll get to a point where we see that there is one item left. So if we added all of these up, we know that we should get some kind of sigma I, okay, because we were going 1, 2, 3, 4, 5, all the way up to n minus 1. And so we're going to end up with n minus 1 minus 1 times n all over 2. Okay, and so we know that that gives us something that is order n squared. Okay. So we can see that our bubble sort gives us an n squared operation, n squared complexity in sorting. All right. Okay, so that's the bubble sort, where essentially we are always doing the comparisons of two neighboring items in the list. If they're in the wrong order, we swap them. If they're in the correct order, we leave them as they are, and the loop increments to the next one. Okay. Let's undo our nicely sorted list so that we can then look at the next thing. 61, 13, 12, 5, and 51. All right. Okay, so we've done the bubble sort. We then want to look at, in fact, I just want to show you a website. I will find the connection, a website. I posted a link to it on Moodle. Which will be all the way down here, and comparison-based sorting algorithms. Okay, so you can see on this website, it's actually quite a nice site. It gives you a very nice look at how these different algorithms work. Okay, so you click on randomize the array. So I'm just going to paste that there. Click on randomize array, and then you can see it's got some of the different types of sorts. So if we click on the bubble sort, you can see what it's doing here is it's comparing the neighbors and saying, do they swap? So here, it compares 85 and 51, 85 and 76, 85 and 66, and it continues doing that all the way through. So you can see it picks it up, it does those swaps. If we run it through until there, okay, you can see now when it finds things that are already in the correct order, it leaves them like they are, and so it doesn't actually make a change. And then otherwise, it continues right up until the second last item. Now in the third iteration, you'll see that it stops as soon as it gets to this third last space over here. So if we continue, and you can see that the loop continues like this, and you can see that the rear end of the list is sorted. Okay. All right, so this gives a nice illustration of what the different sorts are doing, and you can see how the list is starting to look sorted. This backside is definitely sorted, and everything else is starting to get there. You can see that it will now continually move these items here forward, especially this 20. The downside to this is that it's doing all of those, you can see that it's doing all of those comparisons every single time. Okay, so we see overall the number of comparisons that it's done is something in n squared. And that gets us here. No, we're not going to do radix sort today. Okay, so that gives us our bubble sort. The next one we're going to look at is the insertion sort. Okay. So the insertion sort works like this. You end up saying we have a list of stuff that is sorted and a list of stuff that is unsorted. Then what we do is, if the first half of the list, so in this case, the first the boundary is over here, and everything on this side is sorted on the left, and everything on the right you can see is unsorted. Then what you do is you pick up a new number and you compare it. So for example, here we see 80, you compare it with 99, and we see they're in the wrong order, and so we then compare it with 90, we then swap them. We then compare the 80 and the 97 and we swap them, and then we compare the 80 and the 95 and we swap. And we continue with those swaps all the way down until we find the correct place for the item that we're busy inserting. Okay. So if we go back here, we can immediately say that one item by itself is sorted. So we've got our 42, and our 42 is sorted like that. All right. We then say, take the next item from the unsorted array and insert it into the sorted array. Okay. So we say that the sorted array grows by 1, and we then say compare 61 and 42. All right. Are they in the correct order? Yes, they are. And so we're just happy. And so we move on to the next one. So we then move over by 1. Okay. We insert the 13 into our sorted list. We say, is the 13 and the 61, are they in the correct order? No, they're not. And so we swap them. Like that. Okay. 13 and 61. We then say, okay, 13 and 42, are those in the correct order? No, they're not. So we swap them. So we get our 42 moving there and our 13 moving there. Okay. So we can see that the 13 has now reached all the way to the front, so it's in the correct place, and we leave it there according to the sorted list. We then take a number from our unsorted section and insert it into the sorted section. So our sorted area grows by 1. We say compare 12 and 61. So compare it to the back of the sorted list. Does it need to swap? Yes, it does, because they're in the wrong order. And so we end up with 12 and then 61. We then say compare 12 and 42. Okay. So those would also need to swap. So we end up swapping them, and we get 12 and 42 in that order. We then do another check, 12 and 13, and we see that those are in the incorrect order, and so those must definitely swap as well. So we've now inserted 12 into its correct place. Okay. Next thing we do, we take an item from the unsorted section and we add it to the sorted section. And so we just continue with the algorithm like this until we've added every single item into the sorted part of the array. Okay, so when inserting 5, we compare it to 61 and we see that they must swap. Then we compare 5 and 42 and we see that they must swap. Then we compare 5 and 13 and we see that those are in the wrong element, and so those must swap. We then see 5 and 12. We compare those. We see they're in the wrong order, and so those must also swap. All right. There we then take the final unsorted item. We take it, we insert it into the list. Okay. And so 51 and 61 swap. We see 51 and 42. Okay, 51 is bigger than, and we know this part of the list is sorted, and so we know that 51 is now in the correct place. We've now run out of new items from our unsorted area to add in, and so it means that the list is now sorted. All right. Okay, so the question is, so insertion sort essentially deals with one element until it's in the right place and then moves on to the next. So it's not necessarily that it puts it into the right place. Rather, think of insertion sort as saying we have an unsorted list and a sorted list, and we take an item from the unsorted list, and then we iterate over the sorted list until we find the correct place to put it into the sorted list. It's not necessarily the correct place for it to be forever. It's just the correct place for it to be now so far. All right. So we have a number. Think about where do we put it. Okay. And that's why it's an insertion sort. So we come up, we pick a number, and then we find the correct place to insert it. So if we go back and maybe let's step forward, let's randomize. Okay. So you can see when it starts off, it's got a completely unsorted list. It says, okay, this first one over here is considered the sorted list. It compares 77 and 36. It says, is the 77 in the correct place? And we'll see that yes, it is. Then it tries to add 39 to the sorted list. And so it compares it to 77, and those should swap. Then it compares 39 and 36, and it says, is it in the correct place? Yes, it is, and so it's fine. It then tries to insert 86 into the sorted list, and so we see that it compares it with 77, and in this case, it's correct, and so it leaves it. The next one is going to be 85, and so then it searches through until it's put it in the correct place. Following that, it's going to pick up the 23, and it's going to say, okay, is 23 less than 86? Yes, it is, and so they swap. Then it's going to say, is 23 less than 85? Yes, it is, and so they swap. Same with 77, same with 39, same with 36. Okay, so we pick up an item from our unsorted list, and we insert it into the correct place in our sorted list. So that's our insertion sort. Okay, if you think about the best and worst case scenarios, which we'll look at for all of them later on, but let's think about how do we measure how much work we've done? Well, let's say in the worst case, what's going to happen is we're going to have a list where we pick up a number, we have to move it all the way to the front of the sorted list. Okay. And then we're going to pick up a new number from our unsorted list, and we're going to move it all the way back to the front. And then we're going to pick up another one from our unsorted list and move it all the way back to the front, and another, and another, and another. So essentially, for our insertion sort, okay, on our first iteration, we're saying we would say in this first iteration, okay, we would have to compare it with the one item in our sorted list. In our second iteration, we're saying we would have to swap and move it all the way to the very front of our sorted list. So in this case, we would then do 2, because they're now 2 items. In our third, we would do 3. In our fourth, we would do 4. And we would continue like that all the way up to n-1, right? In which case, we would do n-1 comparisons, okay? And so if we sum up the number of comparisons that we've done in total, that will give us sigma I again. I goes from 1 up to n-1. And so that's going to give us n-1 times n all over 2. Okay. Which we see actually was exactly the same as what we said for our bubble sort. So we see that our insertion sort is not actually much better. Okay. In this general case, okay, we will think about our best and worst case scenarios later when we've done our next one as well. Okay, so no questions so far. Okay, so that's our bubble sort and our insertion sort done. The next one we're going to look at is something called a selection sort. Okay, so if we want to look at the animation of this running again, essentially what you do with a selection sort is you find the next number that you want to insert into the sorted list. So in the insertion sort, we had a sorted half and an unsorted half. And then we always just took the first number from the unsorted part and inserted it into the correct place in the sorted list. With the selection sort, what you do is you search through the unsorted part to find the next number to insert. So you can see what we're doing is you scan through the unsorted section and you look for the minimum number. So you can see that they're always keeping track of the minimum number here.
And then once you found that minimum number, okay, so as they scan through, yeah, you can see they found the minimum number is 54. And then what they're going to do is they're going to say, take the 54 and swap it with the item that is the first one in the unsorted list. So in this case, it's going to swap it with 74. Okay, so you can see 54 and 74 have now swapped. And so now we say that the 54 has been added to the sorted list. All right. So for a selection sort, what you're doing is you have a sorted and unsorted section of your list, and you search through the unsorted section. You select the item that is the smallest, and then you insert it into the sorted list. So if we go back to here, I'm just going to unsort this list, undo, 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 undo. Okay. So say that this is the list that we've got. Okay. So the first thing we do is we start off with our sorted list, which is empty, and our unsorted list, which has all the items in it. Our selection sort then says we need to remember the minimum number that we've seen so far. Okay, so the first one we look at is 42, and we say, okay, that's the smallest number we've seen so far. Following that, we look at the 61, and we say, is it less than our minimum? No, it's not, so we leave it. We then compare with 13. We say, is it less than the minimum we found so far? Yes, it is. So we say that 13 is our new minimum. We then compare with 12. Is it less than our minimum? Yes, it is. And so 12 is now our minimum. We then compare with the 5. We say, is that less? Yes, it is. And so 5 is our new minimum. And then we compare with 51, and 5 is still smaller. And so that's it. We found our minimum value for this. We then say we want to move our sorted pointer over by 1. Okay, so we can move that up, and we say that the 5 and the 42 then must swap. Okay. 42 have swapped. Okay, so now our 5 has been added to the sorted list, and that's now in the correct place. We then start at the beginning of our unsorted list again, and we say, look for the minimum value. So currently it's 61. That's the smallest one we've seen so far in our unsorted list. We then look at 13, and we say, is it smaller than our minimum? Yes, it is. So 13 is the new minimum. Then we look at 12, and we say, is it less than our current minimum? Yes, it is. And so 12 becomes our new minimum. We then go to the next one, and we see 42. Is it less than our minimum? No, it's not. We look at the next one, we see 51. Is it less than our minimum? No, it's not. So we've reached the end of our unsorted list. And so we know that 12 is the next one we've got. So we then want to insert that into our unsorted list. So we say that our unsorted list is now 1 item bigger, and we swap with this item, the 61. So now we have our sorted list with 2 items in it, and our unsorted list with the 4 items in it. We then go back, and we say, let's find the minimum item from our unsorted list. So we start at the beginning of the unsorted list. We see a 13. We say, okay, compare it to the next thing. Okay, so we get to 61. Is 61 less than our current minimum? No, it's not. So it stays the same. We go to the next one. Is 42 less than our current minimum? No, it's not. So it stays the same. Is 51 less than our current minimum? No, it's not. So it stays the same. So we now know that 13 is our current minimum. And so we would swap 13 with itself, okay, which would end up just leaving it there. Our next iteration says 61 is the minimum that we've seen so far. Okay, we move on to the next item. We see 42. Is 42 less than 61? Yes, it is. And so 42 is now our minimum value. Okay. Is 51 less than 42? No, it's not. Okay, so 42 stays the minimum. All right, so we've now reached the end of our unsorted list. We want to insert the 42 into our sorted list, so that moves up by 1. And we then say swap 42 and 61. And now our 42 has been added into our sorted list. Okay. We now look for the minimum number in the remaining unsorted list. So we start at the beginning. We say 61 is the smallest number we've seen so far. From there, we compare it with our next item, 51. And we say, is 51 less than 61? Yes, it is. And so that becomes our minimum number. Then we say, we've reached the end of our unsorted list. Okay, so we want to insert that into the sorted part. Okay, and so we end up swapping 51 and 61. Following that, this is now all sorted, and this is our unsorted section. When we see that there's only one item left in our unsorted section, it means that we're finished, because this is obviously then the minimum number, and so you can just say that one gets added to the sorted list, and you can see it's now all completely sorted. All right, so if there are any questions. Okay, so does the selection sort look inefficient? Okay, so if we look at the number of comparisons that we're doing, okay, let's think about the worst case. So what happens is we would say that if the list is sorted backwards, okay, that would mean that we pick a number, then our smallest number is going to be the one right at the back, okay, that we then swap in to get the correct, to put it in the correct position. Then we scan all the way through, find our smallest number, put it in. Scan all the way through, scan all the way through, scan all the way through. And actually we'll find that it doesn't actually matter how many, what that order is. That for our selection sort, okay, we start off with n items in total. We have one item in we have 0 items in our sorted list. And so we then need to say, okay, 3 is our minimum value, compare it with everything else. So we do, in our first iteration, we do n-1 comparisons. Okay. In our second iteration, we then say we say one item is in our smallest in our sorted array, and the remaining n-1 items we need to find the minimum. And in order to do that, we do n-2 comparisons. In the next one, we do n-3 comparisons. In the next one, we do n-4 comparisons. Okay. And then finally, when we're on n-2, n-1, all right, in this very last one, we would end up doing 0 comparisons, because we would know that when you have one item, then there's nothing to compare it to. There would only be one item left in the unsorted list. And similarly, in n-2 case, we would end up doing 1. Okay, is that correct? Okay, let's see. Yeah, cool. Okay, so if we wanted to total up the total number of comparisons that we end up doing, we can see that it's just sigma I up to n-1, which turns out to be exactly the same as the insertion sort. Okay, so the sigma I sits like that, and we end up doing n-1 times n over 2 comparisons, which is also n squared. Okay, so we see that these 3 sorts are basically equivalent. We see that in terms of their complexity, ultimately we're ending up doing the same number of overall operations each time. Okay, essentially we can say, sorry, where's my thing? So there are some special escape clauses that you can add to maybe make 1 or 2 of them more efficient in some cases. But in general, if you don't have these things that are specifically looking to say, okay, is the list now finished? Is it sorted at every step? Then each of these will just run the set n-1 n over 2 times, and you'll find that you'll get this fixed number of comparisons in each time. Okay, so all of these things end up being n squared. If we adapted the algorithm to say, okay, if we don't need to do a swap, okay, at all, then it means the list is sorted. So, for example, with an insertion sort, we actually do quite a lot better. So the insertion sort, sorry, in fact, yeah, the insertion sort has this. So with the insertion sort, you can see that if the list is already sorted, it means that we do everything in linear time. Because you can see what happens. Insertion sort. Okay. If the list is sorted, we say compare the first one and the second one. Okay. And so that's then fine. They're in the correct order. And so when we're adding the 5 to the sorted list, it's already in the correct place. Same thing with 7. We're adding 7 into the sorted list, and so it's already in the correct place. Same with 9. And so with our insertion sort in general, if the list is already sorted, we do very well. Okay. If the list is in reverse order, however, then we do really badly. And then we end up doing this total number of comparisons every time. Okay. You can add something like this to the bubble sort as well. And you can say, if you do a full main loop iteration without doing any swaps, it means the list is already sorted and that you can stop early. Okay. With the selection sort, so where's our selection sort? Okay. You can see with our selection sort, unfortunately, we end up doing the entire check every time because we have to make sure that we go through and find the minimum number from that unsorted list. So regardless of the structure of our input for our selection sort, we always do badly. Okay, so in general, what you would do is you would say our insertion sort actually seems to do the best of these three. So that's the one I would stick to if you had to use one of these three algorithms. Also, the insertion sort is quite easy to implement, and it's quite straightforward, and so that works nicely. So I'm just going to let the video stream kind of catch up with you guys. And we'll see if there are any questions, and then from there we'll move on to the next sorts. Cool. All right then, so we can move on to some of the next ones. Maybe that other link that I posted on Moodle as well is worth looking at, the sortingalgorithms.com. Okay, and what this does is it gives you a sense of what your best and worst cases are for all of these different things. So we've so far looked at insertion, selection, and bubble sort. Okay, so if we look at the bubble sort on a nearly sorted list, okay, so bubble sort on a nearly sorted list, you can see that because it says if we do an entire iteration, so on the normal one, we do a whole bunch of iterations like this, and you can see that it does all these swaps and all of that. Okay, so what we know is that as soon as our bubble sort has a full iteration where none of these things have swapped, it means that they must already be in the correct order. So we see that a nearly sorted list is a very good case for bubble sort. Okay, a reverse sorted list, on the other hand, is the worst case because you can see that it ends up doing the maximum number of not only comparisons, but the maximum number of swaps as well. Okay, so the reverse sorted list is not a great one. And then we're not so worried about the unique ones at this point. Okay, so we see that the reverse sorted list for bubble sort is the worst case. The nearly sorted or sorted case for bubble sort is the best case. and then the random cases happen as well. Okay. If we compare that to our selection sort with a random list, okay, we see it working as we illustrated on the other site and in PowerPoint. And so you can see it runs through doing its comparisons. However, you see when we have a list that's nearly sorted, there's no clever work that it does here, because all it's doing is searching through the remaining unsorted items to find the minimum value. So when we take that minimum from the unsorted list and then try and add it into the sorted list, we still have to search through all of these different items. Okay, and so you can see it actually takes the same amount of time regardless of whether the list is sorted already or whether the list is reverse sorted. Okay, so unfortunately our selection sort doesn't really have a best case for us. There's no case where it does better than it would otherwise. The insertion sort, okay, if we look at our nearly sorted list, okay, remember we have an unsorted list. We take an item from the unsorted section and we add it into the sorted section. If the list is already in the correct order, then it means that when swapping forward, okay, to insert it into that list, it means we do the minimum number of steps. Okay, when the list is reverse sorted, that's when we have our worst case, and we end up doing the maximum number. As you can see, it has to swap all the way down, all the way back in, and it ends up doing the maximum number of comparisons and the maximum number of swaps. Okay, so the question then is, are there any practical differences between the sorts, or are we just looking for the quickest? So in general, you would want to be looking for the quickest sort. So you want to say, what is the quickest way that we can sort a list of 5 bajillion numbers? Okay, but what we can see is that some of the different sorts have different properties. And so, for example, you'll do really well on a so you'll do really well on like an insertion sort when your list is nearly sorted, but you know that you'll do badly on your nearly sorted list when you're doing a selection sort, for example. And so you would want to try and do this in a way that you can be absolutely sure that that you don't use an algorithm that's going to work out badly on the given data set that you've got. Okay. Yeah. Okay. So what site is this? Okay. So the site with all of these different cases. If you go to Moodle and you scroll all the way to the very bottom, you'll see that there are 2 links that I've put on Moodle. I put them up last night. There's the sorting algorithm animations one, and there's the comparison sorting algorithms one, which are both there. All right. I definitely recommend looking at those, making sure you understand what's happening there. Sorting is one of those fundamental things in computer science that is studied, and so there's some really, really nice algorithms that will that you can look at. Are there any sorting algorithms that will always work out well? So all of these sorting algorithms we'll find have good and bad cases. Well, most of them at least. They have good and bad cases. And so it's hard to say that you can have one that will always, always, always do well. But you can certainly say that there are some that will do well more often than others. And so you definitely want to take that into account when picking one. All right. So in general, of these 3, the one that I would recommend to use is the insertion sort. Okay. Because it does so the selection sort is obviously it always does the same amount of work regardless, so it's always doing that maximum, and so that makes us sad. The bubble sort, you can potentially end up doing a lot of unnecessary swaps. Okay, so while your bubble sort and your insertion sort have similar best and worst cases in terms of the number of comparisons, okay, what you're saying is that your bubble sort, you're always doing a swap when you find an item that's in the wrong order. Whereas with your insertion sort, you're saying you do as few swaps as possible in order to put it into the correct place. Okay, so that gets us our sorting ones. So that's these three. With being n squared, so being an n squared algorithm, okay, it means that it will not perform particularly well on very large data sets. So if you have a data set of 10 or 20 or 30 items, you're okay. But if you have a data set of 1,000 items, then you're not okay. All right. So we can say, in fact, let's have a look here. Let's have a look at it. If we go over here and we say, what does an n squared algorithm look like? Well, if our data set is 10, okay, so equals that times that. Okay, let's make that 20, 30, 40. Okay, so we can have a look and see how that grows. And if we graph it, okay, we can see how the number of comparisons that we're doing in this case is growing quite horribly. Make a line graph rather. Okay. This column. Yes. Okay. There we are. Okay. So you can see that we're kind of okay here when our data is small, but as soon as your data starts to get big, you start to run into problems quite quickly. Okay. And we'll see later when we talk about what sorts you should actually use. We're going to say that the insertion sort is actually a good one to use when you've got really, really small data. So when you're talking about very short lists. But as soon as you're talking about a list that's any bigger than that, then we want to try and say, okay, can we come up with another algorithm that uses something else? Okay. Book from 1968. Nice. Yeah, no, exactly. So you know, the point is that that sorting is something that's very well studied. It's something that's well understood, and it gives you a very nice introduction on how to do a lot of this basic analysis. Okay. So those are our first three basic sorts. Then we've also covered another two sorts, okay, which we know was our AVL sort. Okay. Where are we? Okay, so here we're going to add in our AVL sort and our heap sort. Okay. Our AVL sort, we said you're going to add all your items to an AVL tree. All right. So we said to add an item to an AVL tree takes log n time. Okay, because we know that our AVL tree is balanced. And then in order to add n items, okay, we said that that's going to be n log n. Okay. And then after we've created the AVL tree, we then do an in-order traversal, which gives us the sorted list, correct? So we get an insertion, which is log n time. We do n of them, and then we do our traversal. Okay. And if we talk about this in our big O notation, we would say, okay, which of these two items do we will dominate as n gets big? Okay, and so it would be the n log n. And so we would say that this is an n log n algorithm. Right. So maybe it'll be worth adding that. So let's say we had our n squared. We're going to have n log n. Okay, so let's say log n multiplied by n. Okay, so this is going to be log base 10 and not log base 2, but it will give us a sense of the shape at least. Okay. Which is what we care about at this point. Because remember that our big O notation says that there are constants that we're not looking at. Okay, So first column and first row, next, finish. Okay. So you can see, looking at this graph, that our n log n algorithm is significantly better, right? You can see that after the, have I drawn this right? Yeah. You can see, like, after we get bigger than here, the n squared algorithm starts to get bad quite quickly, while our n log n algorithm actually does very, very well. Okay. And so even if we're looking here, you can see at sorting 1,000 items, you're doing in the order of 1,000,000 operations with an n squared algorithm, and you're doing in the order of 3,000 operations with an n log n algorithm. Okay. So you can see the n log n algorithms really are significantly better. Okay. You guys are a bunch of clowns. Okay, so so that was our AVL sort, and then with our heap sort, okay, that had a similar kind of approach. We said first we construct a binary heap, and then once we've constructed the binary heap, we can then just consistently remove the maximum item from the heap. And so we say, and this is the algorithm that we spoke about but didn't study, okay, we can construct a binary heap in linear time. Okay, there's a very clever algorithm for doing that, but we haven't covered it this year, so don't panic. As long as we know that we can do that in linear time. And then in order to remove an item from a binary heap, we say that it could take logarithmic time to remove an item, correct? And we want to remove n items. So if we do logarithmic time, n times, we're looking at n log n. And so we see that to construct takes n, to remove n times takes n log n, and so our dominating term over all of that is going to be n log n. Okay, and so we see that our AVL sort and our heap sort have the same asymptotic complexity. If we go to, let's have a look. If we go, okay, so I see that this one has, there was one that had both. No, so that doesn't have it. Okay, so this one has a heap sort. So you can see if we run the algorithm, if I can find it, heap sort. Okay, so if we run the algorithm, you can see it creates the heap, and then once it's created the heap, it gets the max and puts it down here. So it creates the heap, get max, get max, get max, get max, get max. Okay, so create the heap, get max, get max, get max, get max. Okay. When creating the heap, get max, get max, get max, get max, get max. Same thing here. Create the heap, get max, get max, get max, get max. Okay. And same over here. Create the heap, get max, get max, get max. And we know that we can represent a binary heap as an array, okay, because we know it's a complete binary tree, and so we don't need any extra space or anything either. So that's our heap sort. There was quite a nice, there was another nice one. It might have been this one. Yeah, it was this one. So you can see, so here, this gives you another idea of the heap sort. I've got the play button in the wrong place. So at the moment, it's creating the heap. And so you can see that's just the algorithm that is running this linear algorithm. Okay, so now it's pulled out the max, and then it does all its rotations to fix, pulls out the max, and then does whatever swaps we need to fix, pulls out the max, does some swaps, 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 pulls out the max, does some swaps. Okay. And so this is quite a nice website actually, because it runs them, runs some of the sorts next to each other, and so you can actually see what's happening. So for example, if we go to a Let's add an insertion sort as well as a bubble sort. Come on. So we've added the insertion sort. We want to add in a bubble sort as well. And let's add in, does it have selection? There we go. Okay, so we've got insertion sort, bubble sort, selection sort, and the heap sort up there as well. Okay, so they are the four sorts. Let's see, does it have an AVL? No, not really. Okay, so there's no AVL sort here, but that's okay. So they are the four sorts. Let's animate them. Okay, and you can see how they're all working at the same time. So you can see the bubble sort moves along and compares two next to each other, compares two next to each other, does a swap, compares two next to each other, does a swap, all of that. Okay. The heap sort is constructing the heap and then continually pulling out get max, get max, get max. Okay. The selection sort is searching through, finding the minimum, and then adding it to the sorted list. And our insertion sort says add to a sorted list, add to a sorted list, add to a sorted list. Okay. So you can see, if we look at the number of comparisons in all of these, you can see our heap sort ended up doing 63, our selection sort did 48, our bubble sort did 63, and our insertion sort did 44. Okay. Now bear in mind that the size of these lists are small enough that they all look more or less comparable. But remember, we're talking about this part of the graph over here, and as the input size of our list grows, this very quickly starts to separate. Okay. So okay, so in order to, so the question is, why is the get max n log n? Okay, and that's because we've got, we say that we can get the maximum number, or we can remove the maximum number from a binary heap in logarithmic time. Okay, so we add all our items to a binary heap, which we say we can do very cleverly in linear time. And then from there, we remove the maximum number. But once we've removed that number, remember, you then have to do, you take the last number that was inserted, you swap it with the root, and then you then take that new item that's the new root, and you compare it with its children, and then compare that with the children, and you keep comparing and swapping down until you put it back in the correct place. And we know that in the worst case, you might have to send that item all the way back down to the bottom of the tree. Okay, and it's a complete tree which has logarithmic height. Okay, so one iteration of get max could take logarithmic time, but they're n items, so we have to remove n items. So we do logarithmic time n times. Okay, so it's essentially for the same reason that constructing the AVL tree took n log n, because you have an operation that takes logarithmic time. Okay, and then we do that operation n times. Same over here. We have our remove operation that takes logarithmic time, and we do that operation n times. Okay. So so far between all of these algorithms, you would probably want to pick either the AVL sort or the heap sort. Okay, because we see that those give us our nice logarithmic time, or our n log n time at least, and then you could maybe implement them and run a whole bunch of different tests on different sorted lists and see when they do well and when they do badly. Okay, so for example, an AVL sort will do better when the structure of your data is such that the AVL tree doesn't have to do lots of rotations, right? So when you insert an item, you only ever have to do, let's say you can just insert it straight without having to do any rotations. Whereas if you had your AVL tree where when you insert an item and then you have to do a rotation to fix, and then you insert an item and you do a rotation to fix, and you insert an item and you do a rotation to fix. And so, for example, the AVL sort will do worse if your list is already sorted, or even reverse sorted, because then you can imagine that your AVL tree is going to start looking like that worst case tree where you always just have one child. Now, because it's an AVL tree, those rotations will make sure that it doesn't stay like that, but it does mean that we're doing extra work. Okay. On the heap sort, okay, it will depend on how long it takes to construct the binary heap, because that while it's linear, sometimes you can do more swaps than others. And then on the removal side, it's if we have a structure such that we have to always swap the root, the idea, you move that item up to the root and then you swap it with its children. And if you have to do that all the way down so that it goes to the bottom every time, then that's when you're doing the most amount of work. Okay. Cool. So that gets us to those two sorts. Okay. Now there are two more sorts that we want to look at, and actually these are the two sorts that are the ultimate ones that you're going to want to use, and that are generally implemented for us. Okay. So the first one, I'm just unsorting our list. Unsort, undo. Okay. Sorry, I'm just going to. Okay, so let's go back to this. Yes, yeah, the video will be up. It'll be up just like the other one is, yeah. Okay, so if we have our list, okay, so we now want to look at something called a merge sort. And then after that, we're going to look at something called a quick sort. Okay. Now, the merge sort and quick sort are both recursive algorithms, which I'm sure you guys will love. And so our system works by saying this. It says we figured out a good way of sorting very small lists. So maybe what we can do is we can split our overall list into a couple of short lists, sort those, and then try and merge them back together in some clever way. Okay, and that's where our merge sort comes from. So think of it like this. If we have two sorted lists, okay, so let's say we have 1, 5, 10, and 13. And then on the other list, let's say we have 0, 2, 3, 7, and 42. Okay. Given these two sorted lists, okay, is there something clever that we can do to merge them back into one long list without doing a lot of work? And the answer to that is yes. Okay. So all we have to do is say, look at the front of each of these lists. And if we say, okay, take the minimum number from each of these. We know that they're sorted, so we can just get it from the front. So we can do this constant, right? So we say, compare these front two, take the minimum. Okay, so in this case, it's 0. So we take the 0 and we insert it into our main list. Okay, we then compare these two. And we'd say, take the minimum. Okay, so we know that the minimum is 1. So we take 1, and that's now the front of this list. We then compare these two. All right? And so we compare 5 and 2. We say 2 is the minimum, and so we insert 2. Okay. We then have 5 and 3. So we take the minimum, 3. We then have 5 and 7. We take the minimum, 5. We then have 10 and 7. We take the minimum, 7. We then have 10 and 42. We take the minimum, 10. We then have 13 and 42. Okay, so we take the minimum. And now list 1 is empty. So we can then just take anything that's remaining in list 2 and move it across. Right. So you can see that what we've done is we've taken 2 short, smaller lists and we've merged them together into one longer list. All right. And that longer list is still sorted. Okay. So you can see that this then is going to be the basis for our next sort, which is called a merge sort. Okay. Where we say that given two sorted lists, we can merge them together in linear time. Okay. So let's go back to what we originally had here with our lists. Okay. Yes, these two small lists both have to be sorted. Okay, that's very important. They must both be sorted. Okay, but if they are both sorted, we can merge them together into one long list very, very efficiently. Okay, and so we can say maybe imagine this case. Let's say we had so rather than 1, 5, 10, 13, then we're going to say that we had 100, 500, 1,000, and 13. Okay, 1,300. Okay, so essentially we can say compare 100 and 0. Okay, that gets us 0. Then 102, 103, 107, 142. Okay, so you can see that if the one list is bigger than the other, okay, we only ever compare the front item to each of the items in that other list. Okay, and so it means that if you assume that each of them has, if they're evenly split between the two lists, okay, that means that in order to merge the two, in this case, we ended up doing n/2 comparisons. Okay. Because the one, we only ever compared the front one with the rest there. Okay. Similarly, if they were mixed, okay, so we had n/2. So if they were more mixed like this, okay, let's count how many comparisons we've done. We've done 1 and 0. Okay, those get compared. Okay, so we've done that comparison and 0 has been removed and inserted into the array. Okay, so if you think about it, 0 was compared with one item, okay, and then it was taken off and moved into the array. Then 1 and 2, okay, we now moved 1 off. Okay, then 2 and 5, we moved 2 off. Okay, 5 and 3, we moved 3 off. Okay, so you can see that in every time we do a comparison, we remove one number from a list. Okay, it is only possible to remove n numbers from these lists in total, right? So because there are only n numbers. So because we're doing that, we know that the maximum number of comparisons that we can possibly do is going to be n-1, okay, no matter what. So we can do better than that if the one list is entirely bigger than the other list. Okay, then we end up doing n/2 comparisons. But in the absolute worst case, where we jump from one list to the other, 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 okay, then you end up with n-1 comparisons. Okay, what's important though is the fact that we know we can do this in linear time. Okay, regardless of the structure of the list. Okay, we know we can merge two lists together in at worst n-1 time. Okay, so that's very important. Now the question is, how do we use this to actually sort two big lists? Because the problem is that we need to get these two sorted sublists. Okay, And so this is the idea where we can start to think of things in terms of trees. Okay. So maybe let's just go. So it's 41, 42, 61, 13, 12, 5, and 51. Okay. Brace yourselves. So we have 1, 2, 3, 4, 5, 6 items. Okay. What we're going to do is we're going to say we want to try and divide this, okay, into 2 small lists. We then want to sort the left-hand list and the right-hand list. And after that, we want to merge the 2 together. Okay. But now we say to ourselves, okay, let's sort this list of 3. Okay. How do we do that? Well, we're going to do this recursively. So we're going to say we're going to perform a merge sort on these 3 items. Okay. So we're going to divide this list in 2 and then try and merge them back together. Okay. So you divide 3 by 2. It doesn't matter whether if you round down, you go there. If you round up, you go here. Okay. So let's say we round up. Okay. It really doesn't matter though. Okay. So we've done this. We now say we want to sort this list of 2 items. Okay. Which we can do recursively by doing another merge sort. So we can call a merge sort on that. We would then say we want to sort this side, okay, which is now just a 42. Okay. So one number by itself, we're going to say it constitutes a sorted list. So 42 is now sorted and 61 is now sorted. Okay. So now we can merge the 2 back together. Okay. And how do we do that merge? Well, we say you look at the front of each list. Okay. So we compare the front of each list. We take the minimum. So we get 42. Okay. That list is now empty. So we then take whatever's left in the second list, which gives us 42 and then 61. All right. This 13 over here, we would want to sort as well. Okay. But we just said that a number by itself constitutes a sorted list. Okay. So that list is sorted. So we can now merge the 2 together in the same way we did with the other one. Right? And how do we do that? Well, you take you compare the front items of each list. Okay. So you simply say, is 13 less than 42? Yes, it is. And so we take the 13. This list is now empty. And so we just add in everything that's left from the other list. And so the 42 and the 61. Easy. Now we do that for this side as well. Okay. So we say we're doing this recursively. So we divide that into 2 smaller lists. We then say sort each of those lists. So we can sort 12 and 15, which we're also going to sort recursively. So we divide that into a smaller list. Okay. We see that 12 and 5 are individual single items. And so we know that those are already sorted. And so we merge them together following our merge algorithm. So we take the first item from each of them and we compare them. We take the minimum, which is 5. We then say, okay, this list is now empty. So we now just insert everything from the next list. So we get our 12. Okay. Similarly, this guy is already sorted. And then we merge the 2 together. Okay. So it looks like that. So what do we get? Well, we simply compare this list and this list. Look at the front items, take the minimum. Okay, so the minimum here is a 5. We then compare the front of each list. So the front of this one is 12. The front of this one is 51. We take the minimum, so we get 12. Okay. Then this list is now empty. So we can now just insert everything from the other list. So 51. Done. Now these 2 lists are sorted. So we perform a merge. So 1 and 2 merge back together like this. Like that. Okay. And now we perform our merge. So what do? We look at the first item in each list, okay? And we compare them. We take the minimum. So we get a 5. Okay, we then say the front of this list is 12, the front of this list is 13. Okay, so we take the minimum. So we get 12. The front of this list is 51, the front of this list is 13. So we take the minimum. So we get 13. We then compare 42 and 51. Okay, so we get 42. We then compare 61 and 51, and so we get 51. And this list is now finished, so we just take whatever's left on this side and we insert it at the back, like that. And you can see we now have a sorted list. Okay. So the idea of a merge sort, so the idea of our merge sort here is that we take our list, we divide it in 2, we recursively sort the left and the right, and then after that, we merge them back together. All right. So now let's try and look at some of the complexity analysis for this. Okay. So what we're going to do is we're going to rather expand our list just to make it power of 2. So n is now a power of 2, and that will just make life a little bit easier for us in our analysis. Okay, so let's do this example again. Okay, let's add in, let's say 10 and 50, like that. All right, so I just want to move this up a little bit so you have some space. So let's think about our splits first. How many times can we do a recursive call? So we divide our list in 2. Then this list gets divided in 2, okay, as does this list. Okay. Then this list gets divided into, this list gets divided into, this one gets divided into as well, as does this last one. Okay. So how many levels of division have we done? Okay. Well, we did our first one. Okay. So we went from our main list, and in fact, maybe a nice way to visualize it is to say we went from our main list into 2 smaller lists, right? Then this list, we also divided into 2 smaller lists. Okay. Same thing on this side over here. Close enough. Okay. So we did the same thing there. Okay, so we did our first division and we got 2 lists. Then we took that list and divided it in 2. We took that list and divided it in 2. And then each of these got divided in 2 again. Okay? Yes, so the whole idea of the merge sort is you do always divide the lists. Okay, so the idea is keep dividing the lists until you have a list of length 1. When you have a list of length 1, it's sorted, and then you can merge it with any other list you need to merge it with. Okay, so we've then done another split here, another split here, another split here, another split here, here, and here, here. Oh, something's gone wrong. Something has gone terribly wrong. No. Okay, I think it's crashed. Okay, but nevertheless, that idea comes through. Okay, so and it's gone. That sucks. Dull. That was not as helpful as I'd hoped. Nope. Okay, but nevertheless, so if we have a list of 8 items, okay, so let's go back to our 8. Yeah? So we have a list of 8 items, and we ask ourselves, how many times can we divide this in 2? Okay, so we say, how's the best way to do this? Maybe, yeah, okay, I'm just going to write it on this. Okay, so we start off with 8, and we divide that by 2. And then, so we have 2 lists of 4, right? We divide that by 2, and then we have 4 lists of 2. And we divide that by 2, and then we have 8 lists of 1. Okay? So we can see, and this works in general, that if n is equal to 2 to the power of k, we can divide it by 2 k times. Okay? And we've seen that before. I mean, that looks a lot like our binary trees, right? So we know then here that the maximum number of divides will be logarithmic, right? Because what we're saying is if n is equal to 2 to the k, it means that k is equal to log base 2 of n, like that. So we know that there's some kind of limit on the number of times we divide. The next question is our mergers. Okay. And so now I want you to think of it in terms of the amount of work we do in each case. If we say we have some function t of n that represents the number of comparisons that we do, okay? What this is going to say is for this level, it's going to say it's the number of comparisons to sort the left-hand side of the list, okay? So t of the left half plus the number of comparisons for the right half plus some linear term. Okay? So we've said you have the number of comparisons for the left, and because it's recursive, we're going to do it like that. The number of comparisons for the right, plus that linear term that we use to merge everything together. So if we have 2 lists, okay? Oh, whoops. So we have the list of those 4 and the list of those 4. To merge them together takes some linear amount of time, okay? When we're on here, okay, then we would have been talking about t over 2, tn over 2, right? And then the left would be half that size, the right would be half that size, and n would be n over 2. And you would keep going down and down and down like that. All right. Now, I'm going to show you the mathematical approach to this first, and then after that, we're going to look at a more intuitive understanding of what this tells us. Okay. So the first thing to say is, what is the size of the left-hand list? Okay. Well, we've said that if the list that we're sorting is n, the size of the left-hand list is n over 2. And the size of the right-hand list is n over 2. Agreed? So it's 2 times t of n over 2. Okay. That's the number of comparisons that we make. Okay. We've then said, okay, let's assume that we're doing our worst case mergers every time. Okay, so let's talk about the worst case, where we've said it's going to be n minus 1. Okay? Or maybe even, yeah, let's leave it at that for now. Okay. So here is a formula. If we can find we then want to know, is t exponential? Is it n squared? Is it logarithmic? Is it n log n? Do we know what kind of thing we can use here? Okay. Now, step one in solving this equation is to go get a degree in maths, and then you'll know how to solve recurrent formula. And there are ways of solving these in ways that are similar to the way you solve differential equations. Okay, but they are different. So what we're going to do for now is we're not going to look at the formal solution to this, because I don't want to distract from what we're actually trying to achieve here. But luckily for us, Wolfram Alpha is amazing. Okay, and Wolfram Alpha will show us the solution to this very easily. Okay, so I've just gone to Wolfram and I've plugged in 2 times t of n over 2 plus n. Okay, the minus 1 we can add in as well, but it doesn't make any giant change. We'll do that change now. So if we say, okay, added the minus 1, Wolfram is busy thinking this through. Okay, and you can see here is the answer. Okay, and so depending on the amount of work that we do in our base case, okay, so for a list of size 1 or a list of size 2, that will be what these parameters C1, where that comes from. Okay. So essentially what we get from this, though, is that if we know that the number of operations that we do to perform the search follows this equation, okay, we know that it follows this equation, and so we know the solution to that equation is going to have this form, okay, with some constant that at this stage we don't really care about. Okay, we know it's a constant, but what we see is that it's some linear term plus n log n. Okay, and it's log base 2. Okay, so from Wolfram Alpha, we can see that that means that t of n is n plus n log n. All right, and so we can see that our merge sort has n log n complexity in time. All right. So let's catch up on questions. And so you need to, at the very least, know this formula. Okay, you need to be able to say that the number of comparisons that we end up doing is related to n in this way, and then we must know that that is going to be an n log n algorithm. Okay, so you certainly do need to know this bit. Okay, having said that, I don't expect you to be able to solve the problem yourself. Okay, the question then is, where does the n over 2 come from? Okay, so if we've said, okay, so we're defining to say that t of n is equal to the number of operations used to sort a list of n items. Okay. Okay, it's as big as it wants to get it. Okay, so if we said that t is the number of operations that we use to sort a list of n items, okay, and then we said that our merge sort has the following steps, okay. The merge sort does, come on, there, okay. Okay, so to sort some list, we said you take the left-hand side, okay, and you sort it. which means that we go from 0 up until n over 2, right? You sort the left-hand side. You then perform a sort of the right-hand side. Okay. And then from there, we merge the lists together. Okay, so this is our basic pseudocode. Okay, this is our overall idea of how to do a merge sort. Okay. So if we look at this, we say, okay, how long does it take to do this operation? Okay, well, it's the time it takes to do this one, plus the time it takes to do this one, plus the time it takes to do this one. Okay, so we said that merge sort on a list of n items takes tn amount of time. Okay, but this here is a list of n over 2 items. Okay, so we would be saying that this does tn over 2 amount of work. Likewise, this one, say, does tn over 2 amount of work. Okay, so we've said that on a list of n, we take tn. So on a list of n over 2, we take tn over 2. Okay, and then finally, merge our things together, we take some linear amount of time. So you could imagine as some linear function, an plus b, whatever those a and b is. Okay, and those will change depending on the structure of your data. So we said in the worst case, that's going to be n minus 1, and in the best case, that's going to be n over 2 as well. Okay, so then we see that the entire amount of time, tn, okay, so the amount of time that it took for this entire thing to run, okay, is going to be tn, which is simply going to be the sum tn over 2 plus tn over 2 plus this linear term. Okay. And when we add those things together, we get this equation over here. Okay. And when you find the solution of this recurrence equation, then you find that you get that value that Wolfram Alpha gave us. Okay. And what we really care about from that solution is that the number of comparisons that we do is order n log n. Okay, and it turns out that actually the constants involved here are very nice. They're quite small, and so this is a very efficient algorithm. Okay. So there is an intuitive approach to understanding this as well. I want to go. Okay, I'm just going to redraw this quickly. So I want it to look like this. So we're going to say we have 42, 61, 13, 12, 5. Oh, I have 2 61s. 3 61s. Okay, well, let's change this. That can be 50, and that can be 84. So 5, 50, 84, and oh my word, 51. Right. So there is our original list. We took that list and we divided it into 2. Right. So we get the first half, which would go up to 12, and then we would get the second half, which would go from 12. Yeah, so we've done that division. Okay. Sorry, my phone keeps turning itself off of silent. Okay, so we've now divided that list into two. We can then divide each of these lists into two. Okay. So we get that, and we get that. And then on this side, we get the same. Sorry, this takes a bit longer than if I was drawing it on a board. Okay, so we've then got that. And then finally, we end up with our lists like that. All right. Then what we do is we say we would want to do a merge, right? So we would merge these two back together in a way that the list is sorted, okay? OCD. Okay, so we merge these back together and we see that 42 and 61 should go like that. Here we would have 12 and then 13. Here we would have 5 and 50, and here we would have 51 and 84, like that. Next, we would merge these two back together and the other two back together, right? So it would end up looking a little bit like this. And what we would do is we would take the front of each list. So we compare 42 and 12, we get 12. Then we compare 42 and 13, we get 13. And now the one list is empty. And so we literally just copy everything in. So 42 and 61 without doing any more comparisons. On the other side, we say compare the front of each of the lists. So 5 and 51 get compared. Okay, so we get 5. We then compare 50 and 51. We then have finished the one list, so we get 51 and 84. Okay, and then finally, we do this merge, and we take the front of each list, so we get the 5. We then compare 12 and 50, so we get 12. We then compare 13 and 50, so we get 13. We compare 42 and 50, so we get 42. We compare 61 and 50, so we get 50. We compare 61 and 51. We compare 61 and 84. And the one list is now finished, and so we just add in everything else. All right. Now, let's think about the amount of work that we actually did. Okay. So these divisions and stuff are all just our recursive calls, so we're not going to think about that for now. However, when you look over here, our merge is where we're actually doing the work, right? So we do our work over here, over here, over here, and over here on this level, okay? How many comparisons do we do, okay? Well, for these two, we do one comparison. For these ones, and for these ones, okay? And we merge them all together. Then for these ones, okay, we could do more. And for these ones, okay, we do more. Okay, so we're doing our comparisons over here and merging everything together. Okay, how many of these levels are there? So we see there's the one level, there's another one, there's another one, and there's another one. Okay, so how many merge levels do we have? Well, we said that's essentially going to be the height of this of the perfect binary tree here, right? So we can say that the number of levels that we're going to have here is going to be log base 2 of n. Okay, assuming that n is some power of 2. Okay, so we've got that. There's our log n. Then on each side, good call, good call. On each side, we've said in total, we're looking at some linear amount in the worst case in every case. So here, there are n numbers that we're thinking about. Here, there are still n numbers that we're thinking about and that we're merging together. Here, there are still n numbers that we're thinking about and merging together. And finally, we get to there. So that gives you kind of a vague, hand-wavy kind of way of coming to that n log n, right? Because we've said that our merge involves n items on this level. It involves n items on this level. It involves n items on this level and n items over here finally. Okay, so you can see there are 8 numbers, even though they're all in their own list. Here, there are 8 numbers, even though they're split between 4 lists. Here, there are 8 numbers, even though they're split between 1 list. And here, there's 8 numbers, even though they're in 1 list. Okay, so that gets us to n amount of work, n amount of work, n amount of work, n amount of work, and there were logarithmic levels, and so that kind of gets us to our n log n time. Okay, so it's very important that you are able to do a merge sort. Okay, if I give you a list of numbers like this, then you must be able to do all the splits like this, and then do all the mergers like this. Okay, that is absolutely the kind of question that you could expect in an exam. Okay, it is then also important to be able to say, I understand why this is an n log n amount of time algorithm. Okay, so we've just gone divide everything up. Okay, sort the left-hand side, sort the right-hand side, merge the 2 lists together. Okay, and so that's a very important thing to be able to do. And so to be able to essentially get from this to this equation here, and then using some kind of magic, we know that it's an n log n algorithm. Okay, and so we can see quite nicely from alpha, and there are mathematical methods of solving these, and there are people that work on this, but you know, don't get bogged down in those details. The idea here is to understand the sort. Okay. Okay, so that is a merge sort. All right, and a merge sort is generally a very efficient sort. Okay, so let's go randomize the array, and to visualize it. Okay, so you can see what it's done is it's taken the list and divided it into sections. Now there's a list of 2. Each of those are sorted. It's merging the 2 together and it puts it back. Now it's got this entire one and it's merging those 2 back together. Then it's going to sort the next list. Okay, so it's now handling the cases of all the individual ones. Now it's merging 2 together. Now it's going to merge it with the 20. Now you have this list of 3 that's sorted, and it's going to merge it with the list of 4 other things. And you can see how they get merged together. And now that list is sorted. Now it's going to do the next one of 7. Okay, 7 or 6 or however many it had. And you can see, so it's doing a merge. Okay, it does the other ones. It puts the merge together. Okay. And now you can see it's merging again. Now it will merge with the other big one. And you can see how the algorithm follows from here. All right. So that is a merge sort. Okay. Here again, it's doing its merge. Okay, so now I'm doing the right-hand side of the list. Okay, and this is all following through in the same way that it was doing before. Every time it drops those blue bars down to the bottom, it's doing a merge of some kind. Okay, now it's merging those 2 lists. Now it's merging those 2 lists. And that's sorted our algorithm, sorted our list. Okay, merge sorts are very good. They're quite efficient. If we look at a list that is already mostly sorted. You can see it does very nicely. Okay. Lists that are sorted in reverse are slightly less nice. Okay, but they work as well. And then there's that case too, which we don't really need to worry about so much. Okay. Where did we now? Okay, I think okay, so there's one more sort that we need to do called a quick sort. Are you guys okay to carry on for another few minutes and just bash that one out as well? And then after that, that's the entire syllabus done. So so do we want to do the next one as well, or are you guys a bit tired, or what would you guys prefer? Cool. Alrighty. So quick sort and then DCS. Okay, cool. Okay, so the next one to do, only if you do. Deal. All right. Save that. Okay. So the quick sort algorithm. Okay. Okay, so what we're going to do is we're going to say a quick sort of your list. Then what we're going to do is you pick one of the numbers from the list, and we're going to call that a pivot. All right. So we pick a pivot. Okay. What we then do is go through the list, and we say that every item that is bigger than the pivot should go to the right-hand side, and every item that is less than the pivot should go to the left-hand side. Okay. And so what we do is we partition our list into two separate lists. Okay. So we're doing a similar kind of thing to what we did with the merge sort. Okay. Except we're now doing it around their values rather than around their position in the array. Okay. So the next step is to partition the list. Okay. Now, by doing this, we can then say that the pivot, okay, which will then sit in its final place, okay, all the numbers to the right-hand side of it must be bigger than the pivot, and all the numbers to the left-hand side must be less than the pivot, okay, which means actually that the pivot is then in the correct place in the list. Okay, the pivot is now in its final resting place. It's not going to move ever again. It can rest in peace there, and we won't touch it again. Okay. So following that, it means that we now just have to sort all the stuff on the right-hand side and sort all the stuff on the left-hand side. Okay. So we then do a recursive sort of the left, and we do a recursive sort of the right. Okay. And that's our quicksort algorithm. Okay, exactly. RIP. Okay. So I'm just going to move the algorithm, the pseudocode down there. And let's see what we do. How do I keep ending up with so many? I thought I fixed all the repetitions in this list. I actually, of all the things I've lost, I miss my mind the most. Okay. There we go. Okay, so now we have our list that we want to sort. All right. So what I want to do is I want to go through and select a pivot. Okay. So in this case, let's randomly choose the number 42, okay, to be our pivot. Okay. So this one is now the pivot. Let's make it green. Okay. So we leave it there for now. Then we look at all of our different values. Okay. And we say, is 61 bigger? Okay. Yes, it is. So 61 must go on the right-hand side. So we fill up from the right. Okay. We then look at the next one, 13, and we see, no, that's less than the pivot, so that must go to the left. We see 12, that's less than the pivot, so it must go to the left. We see 5, that's less than the pivot, so it must go to the left. We see 50, that's bigger than the pivot, and so we go to the right. Then we see 84, that's bigger than the pivot, and so it must also go to the right. Then we see 51, that's bigger than the pivot, and so that must also go to the right. Okay. And so we've now been through the list. Okay. That took us linear time, right? Because we compared 42 to the n-1 other items. Okay. So remember that takes linear time. And then once we've done that, okay, we can see that everything on this side is big, everything on this side is small, and conveniently, there's a space in the middle for us to put our pivot. Okay. 42 is now in the correct place, and it doesn't need to move again. Okay. Following that, we now do a quick sort on the left-hand side, and we do a quick sort on the right-hand side. Okay. So now we're going to randomly select 13 as our pivot. Okay, as our next one. So let's go light blue for that one. All right. And on this side, let's select 51 as our pivot. Okay. So that will stay where it is. We look over here for the left-hand side. We say we see 12. 12 is less than the pivot. Okay. So it goes to the left. See 5, which is less than the pivot, it goes to the left. Okay. We've now finished partitioning the list. Okay. The pivot is now in its final resting place. Okay. It's not going to make any more changes. And so we then do quick sort of the left. Okay. Which will be these two. So we pick a pivot. Okay. So let's say we're going to pick 12. At this point, it doesn't really matter. Okay. And so we then compare it to 5, and we see 5 is less than the pivot, and so 5 goes to the left. And we've now finished with that part of the list. Okay. I'll delete that and leave the pivots where they are. Okay. So that's now a list of 1. We consider a list of 1 to be sorted, and so we leave it as it is. Okay, we can then, our recursive things will all return, and then we'll carry on with sorting the right-hand side. Okay, whoops. We'll carry on sorting the right-hand side. Okay, so we now say we've picked 51 as our pivot. So we go through and look at the values. Okay, so we compare it to 84. We see that 84 is a bigger number, so it goes to the right. We see that 50 is smaller than the pivot, so it goes to the left. See that 61 is bigger than the pivot, and so it goes to the right. Okay, and you see because we just fill up on either side, we end up with this open space in the middle over there. Okay, and so we now have the final place for 51 to sit. Okay. Now we've got 51 over there. Okay, so we then say sort the left-hand side. Okay, well, it's a list of 1, which we consider to be sorted already, and so we leave it. We then sort the right-hand side. Okay, so we pick a pivot. So let's say 61. Okay, we compare it to all the items in the list and do a partition. So we get 84, goes to the right-hand side, and 61 is happy in its place. Okay, so now we finished sorting the left, we finished sorting the right, all of our recursive calls are finished, And if we have a look, 5, 12, 13, 42, 50, 51, 61, 84. So we can see that our list is now sorted. Okay. So there's we've seen the observation, okay, that why are we randomly selecting the first item every time? Okay, and that's the idea here, is that we have to say, okay, well, what is a good strategy for selecting a pivot? Okay, and so what is a good pivot and what is a bad pivot? Okay, we obviously don't want to have to search through the list multiple times to find a nice pivot, because that's going to take us a long time. So we want to have some kind of algorithm that's going to allow us to pick one well. Okay, so let's see what happens if you actually do pick it randomly, or if you pick the first one every time or the last one every time. What happens? Okay, so think about it like this. If we have a list like this, what is the ideal pivot to choose? Okay, and what is the worst pivot to choose? Okay, so let's have a look and see. Go back to blue. Oh, what blue was it? Okay, so if we went through, okay, and let's say that we had some random criteria for selecting a pivot, okay, if we go here and we say, let's randomly select 5 as our pivot, okay, we now go through and do our partition. Okay, so is 42 bigger than or less than? It's bigger than, so it goes to the right. 61 goes to the right. 13 goes to the right. 12 goes to the right. Okay, we don't compare the pivot with itself. 50 goes to the right. 84 goes to the right. 51 goes to the right. Okay. Excuse me. And then finally, our pivot gets inserted. Okay. We would then sort the left-hand side, which is an empty list. We would then sort the right-hand side, okay, which is an unsorted list like that. Say we now went through and randomly selected 12 to be our next pivot. Okay, so we perform a partitioning. So we go through and we see a 51. See an 84. See a 50. We see a 13. We see a 61. We see a 42. Okay? So we've now partitioned, which means we can insert the pivot in its final resting place. Okay. We then randomly go through and select the next pivot. Let's say we pick a 13. Okay. So we compare all our numbers. We say 42 is bigger than. 61 is bigger than. 50 is bigger than. 84 is bigger than. 51 is bigger than. And we've now finished partitioning. And so our pivot can go into its final spot. Okay. Do you see a problem? I hope you see a problem. Okay. If we select the pivot such that the list decreases by 1 every time, do you see that this is essentially just a merge sort or a selection sort? If we have a strategy that somehow selected the minimum number from the unsorted list to be the pivot, or the maximum number to be the pivot, okay? This is the worst case selection, the worst case pivot that we can possibly choose, okay? And so in this case, we end up getting an algorithm where at every level, we've just removed one item, but we've also compared that item to every other item in the list. So the first time we do n-1 comparisons, the second time we do n-2 comparisons, the third time we do n-3 comparisons, the fourth time we do n-4 comparisons, and we keep going like that, okay? And that should look very similar to what we did over here, right? And so we said n-1 comparisons, n-2 comparisons, n-3 comparisons, all the way through down to 1, which gives us an n-squared algorithm. Okay, so this is bad. This is horrible. We don't want that. Okay. But let's look at another case. Okay. Or in fact, let's look at the case we already did, because that was pretty good. Okay. If we select the item that would divide the list in half. Okay. So do you see when we selected 42, the list was divided in half. When we selected here, if we'd selected 12, the list would have been divided in half, right? Over here, if we'd selected, let's say, either 51 or 61, the list would have been divided in half, okay? Which means that we divide every single time, okay? So what this does for us is it says that in that case, it means that, okay, so let's draw these out. So I'm going to put the two algorithms here. Move that one over for now. Okay. We said in the worst case, okay, we picked a pivot, okay, which let's just say takes constant time. Then we partition based on the pivot, which takes linear time. Okay. Now, this was the worst case. So now we've said the left-hand side is an empty list, okay? So we do literally nothing, okay? I suppose you could say you do order 0, okay? You do no work on the left-hand side, but you do t of n-1 on the right-hand side, right? So essentially what we've said, okay, is that in the worst case, we see that the amount of comparisons we do to sort a list of n is going to be some constant, okay, plus some linear function, plus nothing, plus tn-1. Okay? And if we go to our friendly Wolfram alpha, where's it gone? Wolfram alpha, okay, and we say we want to say, let's say 1 plus n plus t of n-1, okay, and we ask Wolfram to solve that for us. Okay, you can see that that gives us an n-squared algorithm, right? So we've got an n-squared there, which is what we came up with ourselves when we said this. Okay, so we can see in the worst case, we get our n-squared, okay? In our best case, maybe let's make a copy of this one. Okay, let's see what happens. In our best case, we pick a pivot, okay, which we're going to say takes constant time. After that, we do a partition based on that pivot. Okay, so we do some linear amount of work. Okay, on the left-hand side, we're then going to say we've divided the list in 2, and for the right-hand side, we're going to say we've divided the list in 2. Okay, so this is for the best case. And so we can see that our recurrence relationship in this case works out to be some constant plus some linear term plus 2 times Tn over 2. Okay. And we recognize that, right? We recognize that from our merge sort. Okay? And so we know that that gives us our logarithmic time. Okay. Okay, so back on Wolfram. Okay, so we know that we get our n log n time for our sort there. So we see that in the worst case, quicksort gets us n squared, and in the best case, quicksort gets us n log n time. All right. So the question then is, can we be sure? Can we find a way to pick a pivot so that we don't end up with a with this worst case? All right. And the answer to that is yes, we can. Okay. Sorry, my throat is. Okay. So one of the problems here is to say, how can we pick a pivot, okay, that is going to give us that we can select in constant time, okay, because we don't want to change our complexity. So we need to be able to select our pivot quickly, but we also want to make sure that our pivot is not going to give us the case where our list is not shrinking, where it's imbalanced. Okay. Do I want some water? It's okay. I'm going through quite a lot of Coke, so I'll survive. Okay, so so one of the ways then that we can say, can we avoid it, is to say, let's consider when it could happen. Okay, so if we always select the minimum item, or if we always select the maximum item. Okay, so one approach is to say, you know what, the odds of always selecting the worst item, if we do actually get a random value, okay, the odds of selecting that is probably actually pretty low. Yeah. So I mean, if you say 1, 2, 3, 4, 5, 6, 7, 8 numbers, okay, and if we actually did pick a random number, okay, the odds of picking the minimum or the maximum is just 2 out of 8, right? So that's relatively small. Okay. So I mean, that's literally a quarter, so 25%. Then if you said, okay, we're okay if we maybe select the maximum or minimum, once or twice in the entire algorithm. Okay. But if you say the odds of selecting the minimum or maximum in the first level and in the second level and in the third level and in the fourth level and the fifth and the sixth and the seventh and the eighth and the ninth and all the way through until we've sorted our list, okay, that shrinks quite substantially. Okay, so you could say that on the first time, okay, the odds of picking the minimum or maximum is going to be 2 out of n. Okay. Then on the second time, you can say the odds of picking the minimum for the left-hand list and the minimum for the right-hand list, okay, is going to be 2 out of n over 2-ish. Okay. And obviously that the actual probabilities there will depend on how the list was partitioned in the first instance. Okay. But essentially what you can say is that the odds of picking the worst one every single time is small enough that we generally think that the algorithm is okay. Okay, so there's one way to do it like that, where you simply say, pick a random index and treat the number at that index as the as the pivot. And then we just hope for the best and hope that overall it will work out nicely. Okay. There is another way to do it where we can say, well, we want to avoid the case where the list only shrinks by 1 or only shrinks by 2 even. Okay. We want to get the case where we can actually sort the left hand and sort the right hand lists. Okay. So one way to do that is to say, let's select 5 numbers. So let's say 1, 2, 3, 4, 5. And then let's find the median value of those 5 numbers. So in this case, you can see we've got 42, 61, 13, 12, and 5. So the median value here is 13. Okay, so the median says that if those 5 numbers were sorted, which one would be in the middle? Okay, and so it says pick 5 numbers, take the median of that, and use that number as your pivot. And that way you're guaranteed that there are at least 2 numbers that must be less than and at least 2 numbers that must be bigger than. And all the other numbers in the list will have to sit one way or the other. But it means that your worst case is guaranteed not to happen. It means you're guaranteed to get to the point where you can still sort the left-hand side and you can still sort the right-hand side of the list. Okay. And that turns out to be a fairly common strategy by taking the median of 5. And by doing that, by saying we're always using 5, it's still some constant amount of time. Okay, it doesn't vary according to the size of the list, unless obviously n is less than 5, in which case we'd have to do something. But we care more about what happens when n is very big. Okay, so we're saying take 5 items, get the median of those 5, do the partition based on that one, and then do the sort. Okay, and it turns out that in general we can avoid doing n squared amount of work. We can avoid that case such that on average, so the average case, we'll always end up with logarithmic time, or n log n rather, sorry. Okay, so that gets us to the end of quicksort. Okay, you can see that the analysis is fairly similar. We write it out in terms of its recurrence relation, where we say this line does some set amount of work, this line does some linear amount of work, and this line does t of n minus 1 or t of n over 2 or something like that. And in general, that's how you do analysis for recursive algorithms. Okay, and you'll see that there are some very, very clever recursive algorithms, and the analysis is done like this. And you'll find that in honors, you'll do quite a lot of that. But at this point, you know, you're not expected to be able to solve these equations. But I do want you to be able to say, I do require that you can reason out that the worst case of quicksort is n squared. Okay, and you can do that by comparing it to the insertion sort, or by writing it out in terms of sigma or something like that. And that the base case is n log n, and that we know that because we know the solution of t of n equals t of n over 2 plus some linear function. All right. So now in terms of which one you should actually use, okay, largely it varies according to what the structure of your data is. Okay, and so it can be hard to choose sometimes, but in general, what people have found is that an insertion sort is very good for small lists, so very short lists, so something less than 100 items, for example. Just use an insertion sort. It's not a complicated algorithm. It's quick and easy to program. It's very simple, and on top of that, there's very little overhead in terms of the algorithm having to do other things. You know, if you think about a quicksort, it's spending time doing partitions and picking a good pivot and doing your recursive calls. So it's spending some time on that. which for a list of 100 items is not strictly necessary. As your list grows, though, we then very quickly find that the n log n algorithms get better. Okay, so if we go back to this graph, we can see that our n log n ones are certainly the ones we want to be using here, but maybe over here it turns out that the n squared algorithm is fine and that it actually has less overhead there. So often what they do is an implementation will say, if the number of items in the list is below some threshold, then do an insertion sort. And if it's above that threshold, do a quick sort. All right. And in fact, for even like the libraries inside Java and C++, they'll often do things similar to that, where your list could say, like your sort could say, if n is less than some threshold, then do an insertion sort. Yeah. Otherwise, do the normal quick sort. Okay. And so the idea is you can then use a couple of the different algorithms together in order to get you your best efficiency. And that is done in various libraries, and it works very nicely. Okay. So generally, my advice would be to go with a quick sort that's connected to an insertion sort. If you have to only pick one, then I would do a quick sort. And those give you, as long as you know that you're picking a good pivot. All right. Then, so finally, if we go to here and we randomize the array and we do a quick sort, you can see how it's picked a pivot. It's then doing the partitioning, where it's moving items to one side or the other, and then you can see it now does a recursive step where it's now recursively sorting the other list. Here you can see it's picked another pivot. It's now doing its partitioning. Okay, and now we do a recursive sort of quick sort of the left. Okay, recursive quick sort of the left. Okay, now we do a recursive sort of the right. You can see it's busy partitioning, does all its sorting, and then all of that. Okay. And there's our sorted list. All right. There is one other final sort that is worth knowing, and it's called a shell sort. Okay. And a shell sort is generally not great for very small lists or for very big lists. But if you have some kind of medium-sized list, then you find that the shell sort can start to do quite well. But we're not going to study it ourselves. But it is just worth knowing. So essentially, the three sorts that you should keep in your toolbox are the insertion sort, the shell sort, and the quick sort. All right. That brings us to the end of everything, actually. We've now covered the entire syllabus. And so that's everything that you need to know for the exam. In terms of sorting for the exam, you need to know insertion, selection, and bubble sort. Okay. You need to know quick sort and merge sort. You need to know their associated complexities. Okay. And you need to be able to actually perform the sorts. All right. So I might do stuff like, say, given some piece of code, what kind of sort do you think this is? Or I might say, here is a list of numbers, perform a selection sort on that list of numbers. All right. And then I might ask you questions about the complexity of the sort as well. All right. Are there any further questions? We'll just wait for the video to catch up with real time, and then if there are any questions, you can ask them on IRC. Okay, so for the for the lab exam, you will need to know how to implement linked lists, stacks, queues. You need to know how to implement binary trees, binary search trees. Okay. You need to know how to implement a binary heap. Okay. And I'm prepared to tell you already that I will ask you to implement a binary heap. Okay. The others I will do, there'll be bits and pieces. So I might give you a linked list and then say implement the traversal function or implement a delete function of a linked list, for example. Or for trees, I might say implement this traversal and implement the delete function or something. For the binary heap, which is a type of priority queue. Yeah, so for the binary heap, I would say, be able to implement the insert an item and the pop max. All right, and you would need to be able to do the relevant swaps and stuff to be able to do that. So yeah. Okay, so for quicksort and for merge sort, it is possible to do them in place. You don't necessarily need a new array. Okay, so you can do them using no extra memory in terms of storing all of your numbers. Yeah. Yes, lab exam is this this Thursday afternoon. Okay. And I'll give you 3 hours for the lab exam. It will be closed book. The internet will be turned off and all of that. Moodle will actually be deactivated. Okay. And so you won't have access to Moodle either, but there will be a submission on a separate exam Moodle that we have. Okay, do we assume that we're always using a max priority queue? No. Sometimes it could be a min, where it gives you the minimum every time. And that's the same idea for a heap. So it could be a max heap or a min heap, depending on whether it gives you the maximum or minimum. And so just be careful of that. So if I tell you implement a min heap or a min priority queue, then make sure it gives you the minimum. If I say implement a max heap or a max priority queue, then obviously make sure it gives you the maximum. And that goes for the exam as well. If I ask for information about what is the heap condition for a max heap or a min heap, make sure that you get those in the right order. Okay. Cool. Okay, so if there aren't any more questions, I think we can say we can leave it there. Thanks for watching. I hope that this managed to get everything through, that you understand everything. On Monday next week, we will do a revision lecture. Okay, so I will. So bring questions, bring any issues you have, any questions you have, anything you want me to go over, because I will go through everything that's in the exam with you guys again, so we can do a quick revision of everything. Okay, I would definitely recommend coming next Monday. It's not, the last lecture before an exam is always the one you want to be at. So, yeah. Okay, so let's leave that there, and enjoy the rest of your time, the rest of your day. Cool.